The objective in this lab is to analyze an object falling from rest, one that experiences significant drag force. A model is constructed using Newton's second law and the equation for drag force. The models predict that when drag is introduced, the object experiences slower acceleration. This is borne out by observation. My example system is a badminton shuttlecock dropped from a height and falling just under 1.52 meters. Point masses were placed at the approximate middle of the visible band of tape that surrounds the rubber bottom, so the distance the shuttle travels by each frame can be calculated. The calibration stick measures the length of the tape measure hung from the banister. The center of the axis is placed in the first frame at the same point as the point mass of the system for that frame, and the axes are rotated to account for the minor tilt in the camera angle. The parameters for my Python model of the situation are the mass of the object, 0.005 kilograms, the initial position and velocity, both 0, the drag constant, b, and the change in time, or delta t. Based on these parameter inputs, my model computes the shuttle's position plotted against time. To model the position, we use Newton's second law, as in the previous lab, in conjunction with an equation for modeling the drag force. To improve the precision of the model, we say that the drag force varies directly as the square of the magnitude of the shuttle's velocity, rather than as the magnitude itself. To model this in Python, we can create a new variable for the velocity squared, svel squared, which equals the magnitude of the velocity squared. Then the magnitude of the drag force equals the negative of b, the drag constant, times svel squared. The drag force then equals j hat, the direction, times the magnitude of the drag force. Running the program with b equal to 0, we get a graph with no blue arrow for the drag force, but only a yellow arrow for the gravity. Running our program with the b constant, we get a model with a blue arrow for the drag force, which counteracts the yellow arrow for the gravity force. The two graphs for the models are similar, but graphing them in a spreadsheet exposes the differences between them. We can see that the different plots we have look as we might expect. The model disregarding the drag force, in red, falls faster than the model accounting for drag, in yellow, which very closely approximates the values we obtained from tracker, in blue. The initial values from tracker do suggest that the shuttle falls more slowly than how we predicted from the model, but seeing as it happens for only about 1/10 of a second, it may still have been in contact with my hand or the beach towel behind it, causing friction, which would slow down the rate of change of velocity. The two models are different. The drag-free model in red has constant acceleration. In the second model, yellow, the acceleration varies inversely with the velocity. This is because the net force is the sum of the downward gravitational force and the upward drag force. In turn, the drag force increases with increasing velocity. Thus, the net acceleration keeps decreasing as the object increases in speed. A point of equilibrium will be reached when the net force and net acceleration are equal. At this point, the object has terminal velocity. Since terminal velocity can only be reached with drag force, terminal velocity will only be reached in the model with drag force. But we can see that not enough time has passed for the shuttle to reach terminal velocity, as neither the curves for the model nor predicted values have a constant slope quite yet. Note that the terminal velocity is independent of the initial velocity, so even if the shuttle were thrown downwards instead of dropped, it would still eventually reach the same terminal velocity.